So hello everyone, welcome to the HPL seminar. Today, I am pleased to introduce our speaker, Dr. Ryan Schroeder. Ryan got his Bachelor of Science degree in 2013 at the University of Nevada, Mechanical Engineering. In his college, he worked on how to improve the image processing capabilities using MATLAB code for X-ray motion analysis and tracking to assess joint laxity in guinea pig knee. Then he started master's course at the same university under the supervision of Dr. David Lee, specialized in dynamics and controls. During his master's, Ryan primarily worked on designing a biomimetic testing platform for actuators in a series elastic co-contraction system. After he received a master's degree in 2014, he came here to the University of Calgary and started a PhD course in biomedical engineering under the supervision of Dr. John Bertram and Dr. James Croft. Ryan's thesis topic was about gate entrainment in coupled oscillator systems, clarifying the role of the energy optimization in human walking. Is this just me hearing the feedback now?
It's a fun effect.
There was some feedback, but maybe I think let's have Ryan start and then see if that's
Ryan start.
Yeah.
And then see if that's
Oh boy,
it's you.
oh boy.
It's you.
And then I'll just keep going.
Should I start anyway, or?
I'll just keep going.
It's almost
Should
done.
I start anyway, or? It's almost done.
So anyway, Ryan is now currently doing a postdoc working with Dr. Art Kuo, specifically working on human biomechanics and optimization modeling. Ryan also introduced himself as a ping pong enthusiast and a fan of the Las Vegas Raiders, an American football team, and touring musician. Today, Ryan will be giving a talk entitled Passive Loss and Active Cost in Spring Mass Model of Running. All yours, Ryan.
Okay, great. Thanks, Jingwan, for that introduction. Hopefully I'm not echoing too badly. Just going to share my screen here. Okay, you can see the right side of the presentation?
Yes.
Great. So yeah, anyone who's run a long distance or run a marathon knows that running takes a lot of energy. And in fact, we also know that as you increase running speed, you consume more energy per time. So you can imagine that if there is a limit on how much energy you can consume per time, then this might also influence things like your max running speed, which, of course, if you're running a race, directly influences your performance in that race. So energy consumption can be pretty important in this regard, as well as other regards. And yet, despite that, we don't really have a lot of good models for the energetics of running, at least not that accurately predict energetics. And of course, mechanics are really important to understanding mechanisms that influence the energetics. And so any such model should be able to not only predict the energetics of running, but also the general mechanics of running gait as well. And then there are a lot of different types of experimental observations or experimental studies that people will do. Say, for example, here in the HPL, perhaps maybe people are interested in, what's the energetic cost of running with different shoes, and maybe how you can save energy by designing a particular shoe based off its weight, stiffness, heel thickness, things like that. Another question people might be interested in is, well, what's the difference between energetics of running rear foot and forefoot? I feel like it's always only a matter of time in these seminars where the forefoot running thing comes up. And the only point I'll make is that although you could certainly just run the experiment, do the analysis, collect all the data, and see what the result is of your new running shoe, for example, rigorous physics modeling can help you to maybe guide that process, right? So maybe you have a hypothesis and then you test that in the model and then you see if the physics supports what you think ought to happen. And from there you can go ahead with the experiment. And so maybe it helps save some time in the prototyping process and these sorts of things in understanding these sort of fundamental physics principles behind why a given design might work. So this is an example of a study where basically what they did is they took a bunch of different muscle energetics models out in the literature, and they applied them to 8 different muscles operating on a multiple rigid body biomechanical model of walking uphill and downhill and at different speeds. And then they calculated the cost of their energetics models and compared that to the metabolic cost of humans doing similar tasks. And then they compared that for all these different versions of the model. And it turned out, so each one of these plots is comparing the measured metabolic rate, or I guess it's not rate, but measured metabolic cost, so say energy per step, versus what was calculated from the model. And in fact, most of these complex models didn't really do a great job of accurately predicting cost. And in fact, the one that did do a fairly decent job was just simply the work divided by muscle efficiencies. This was an observation by Margarita in 1968 that muscles performing positive work operated around a 25% efficiency and doing negative work at a negative 120% efficiency. So just the simplest version of this cost model actually did the best in terms of predicting energetics of in this case, walking uphill or downhill. So the only point being that more complex model doesn't always necessarily mean that it's going to be better at accurately predicting energetics or mechanics. So way on the other side of the spectrum, a really common model for modeling the mechanics of running is the so-called spring mass model, where all the inertia of the body is sort of lumped into a single point mass, thought of as the center of mass of the body. And then the leg is just modeled as this spring-like leg. And the idea is that as you come into contact with the ground, the leg compresses, force increases, and then the leg extends, force decreases until the body is launched off the ground into a flight phase, and then the process repeats itself. So why do people think that springs might be important? Well, one of the things people have argued is that if you just consider the work done on the center of mass by ground reaction forces during running, and you compare that to the metabolic cost associated with that running, you get this apparent efficiencies that are quite high, in fact. So ranging from 50 to 80% in running for the positive work done by these ground reaction forces. Now, of course, if all that work was being done by the muscle, these efficiencies would be extremely high relative to previous estimates of muscle efficiency, as I mentioned, 25%. So it was thought that it perhaps might have to do with the fact that maybe the spring is doing some of the positive work as well, and therefore your apparent efficiency is not capturing only what the muscle is doing. So this was sort of like an early hint that maybe springs might be doing something here and having an impact. Another study, this was by Roberts in 1997, showing the shortening work of a muscle tendon unit in turkeys, basically partitioning the positive work done by the tendon itself, so energy recovered by the tendon versus the muscle shortening work, positive shortening work. And so a majority of the positive work done was from the elastic tendon, so hinting at this idea that, well, perhaps if the tendon wasn't doing this positive work, then the muscle would have to do more work to compensate, and therefore this tendon was perceived to be doing the majority of the work, allowing the muscles to stay at, closer to near isometric levels or low velocities and do less of this work. So the other reason people like the spring mass model is because it's pretty good at predicting certain aspects of the mechanics of running. So it's pretty good at predicting ground reaction forces, the power of the leg, right? So the rate of work or the rate of energy in the spring, And this is also like thinking of center of mass work, so that the spring is doing this work on the body. It does miss some of the transients in the beginning. You can see in the grayed out human data, some of these extra squiggles, but sort of captures the general trend of the time series. Another metric people look at a lot is this thing. I'm just going to call it a vertical work loop in quotes, because it's not truly a work loop, but it's the vertical acceleration of the body plotted against the vertical displacement of the body. And the idea is that in the spring mass model, you get this very linear looking curve, of which the slope represents the stiffness of the leg. And that kind of rings true with the human data, except that you also have these sort of nonlinear fluctuations about that average slope of the stiffness. So I give it half a check mark. It kind of captures some of it, but is also missing some aspects. And then what about energetics? So here we're looking at the cost of transport against ground slope. So positive values meaning running uphill, negative values running downhill. And as Margarita pointed out all those decades ago, the cost of human running increases with slope in either direction, and sort of asymptotes at the efficiency of muscle 25% in the positive direction, negative 120% in the negative direction. But of course, the spring mass is a conservative system. It's just a spring, so it doesn't consume any energy, at least not from a work basis. And so actually its cost is zero. So basically the spring mass model does a pretty decent job at reproducing basic running mechanics, but doesn't do such a great job with predicting energetics, and it can't do net negative work at all. So it can't even begin to run uphill or downhill. So what are we going to do about this? Well, one simple alternative is we could just replace the spring with an extending actuator that can basically actively extend the leg or can resist compression. And in this case, we say, let's just minimize the amount of work done by the actuator as well as the amount of force done by the actuator. If we only minimize the amount of work done by this actuator, what we get is this extremely impulsive force. So I'll just pull up the laser pointer here. So this arrow just represents an instantaneous force that immediately redirects the body from falling to rising. And so it basically spends the entire step just flying through the air, except for these immediate interactions with the ground. Of course, this means that you lost the energy of the body as it interacted with the ground, and then you replace it with the same amount of positive work so that it could continue on in its periodic gait. And the vertical work loop is infinitely stiff in this sense. Now, if you might be forgiven for just thinking that this looks nothing like the solutions of the spring mass model, so it's entirely different. But in fact, you could imagine that the spring in the leg is of infinite stiffness, and in which case you'd basically get the exact same solution. Now, on the other end of the spectrum, you could imagine having a really compliant spring in the leg. And then in that case, you might have something what we'd call a grounded run. So the body never leaves the ground. And the entire step is spent with the leg in contact with the ground. And then in this case, you have lower peak forces, lower peak power, and a shallower vertical work loop. But it turns out that you can actually basically replicate the solution in the actuator-only model if you also include this force rate cost. And so if force rate is a really high cost, then you also get this grounded run solution. And in fact, you can even get every solution in between these two extremes. And in fact, they look nearly identical in both cases. And just to sort of put a point of emphasis on this, if you look at the vertical work loop of the actuator-only model, you almost even get this sort of pseudo-stiffness, a linear vertical work loop curve with almost no hysteresis, even though there's no spring in the leg. So the actuator is acting kind of like a spring, even though it's not actually a spring. And in both cases, you're really just adjusting a single parameter to adjust where on this spectrum of gates you are. So in the case of the spring mass model, you can increase stiffness of the spring to get a more impulsive force. In the actuator-only model, you're reducing the effective force rate to get a more impulsive force. Okay, so given that both of these models can kind of do the same thing, so long as they're tuned appropriately, they basically get the same grade for producing ground reaction forces, power, this vertical work loop. And of course, the actuator-only model can also do net work because it has an actuator. So what about energetic cost? Well, if we look again at the Margarita plots, so cost of transport against ground slope, we see that the model kind of gets the shape right. It has a bit of the asymptoting towards the ISO efficiency lines and the transition between the two. But in general, cost is quite a bit higher than it should be. And in fact, it's about twice as costly as it is on the level ground. So maybe it gets another half grade, right? Because at least it's not zero cost. It does have some shape to it. It does have some cost, but the cost isn't perfect either. In general, it's overestimating cost quite a bit. Okay, so what are we going to do? Again, the objective is to find a nice simple model that can reproduce the mechanics and energetics of running gates. So we'll propose a model to do this, and we'll test it with two of these costs that I've mentioned before independently to see their effects independently. And we'll test this on flat ground as well as sloped ground, whilst conducting some parameter variation to see what is the effect of varying any particular parameter, essentially a sensitivity analysis. Well, what is our proposed model? It's kind of a combination of the two. So we retain the extensive actuator. We place a spring in series with that actuator. And then on top of that, we add some additional elements. We add some dissipation that are happening in different ways. So we have a damper in parallel with the spring that acts during the compression phase of the spring. And this is supposed to represent hysteresis of a tendon. And then we also consider that when the heel lands on the ground, that foot had some velocity, and then once it's on the ground, it has no more velocity. So it lost some of its momentum and some of its kinetic energy. And so this collision loss also dissipates some energy. Now, why do we include this dissipation? Well, we can look at some in vivo measurements of the Achilles tendon during human hopping. So we're looking at the tendon's force versus its length change for 10 different subjects. And we get measures of hysteresis somewhere between 17 and 35%. So tendons are decent springs, but they're not perfect springs. They do have some losses in them, and we think that could play a role. Furthermore, Ryan Riddick and Art Kuo have shown in a couple of papers that dissipation plays a pretty prominent role in running, and in fact that the majority of the cost in running is simply work to overcome this dissipation and maintain a limit cycle. I'll also note that there are others in the HPL who are working on this issue of passive dissipation experimentally. For example, Kuhn Lemaire and Zhao Yu Fu, and others as well. So we include dissipation, and we're operating this optimization problem. As I mentioned, the cost is going to be made up of primarily these two different costs: the cost of the actuator performing work, as well as the cost of the actuator developing force over time. And then we're controlling the length changes of the actuator in order to minimize that cost. So we'll simulate running over a range of speeds, spring stiffnesses, and slopes. And then we'll prescribe step length and step frequency per a given speed such that it approximately matches something like what humans do. Okay, so we'll begin with applying the model with only minimizing work. So only a work cost, no force rate cost. And we'll choose a spring to do this, a relatively compliant spring actually. And basically we have a single humped ground reaction, vertical ground reaction force. It looks a little bit like some of the other force profiles we've seen in the other models, but looks some slight nuances to the shape of it. And then there's a collision impulse, right? Because we said that some momentum was lost in the foot. So this contributes to the ground reaction force as well. We also have some loss associated with that collision. So when we look at the power of the leg, we lose a bit of energy instantaneously at heel strike. And then the power curve continues on. The actuator does some power, some positive power. And then if we look at the vertical work loop, again, the collision impulse is in there, and we have a relatively shallow vertical work loop for the rest of stance. We can look at the same measures for a relatively stiff spring, and the main difference is just that everything kind of gets stretched. So in the horizontal direction, everything gets compressed for the stiffer spring, and in the vertical direction, it gets stretched, where we have larger peak forces, larger peak power, and steeper vertical work loop curves for the stiffer spring. But in both cases, the actuator is only doing positive work, so that's the blue shaded area. And in fact, the actuator is doing precisely the amount of positive work to overcome dissipation. But in fact, when we look at some data, for example, in vivo measurements of the vastus lateralis during running, in the plot, we're showing the muscle tendon unit, length changes of the muscle tendon unit over time, and then length changes of the muscle fascicle specifically in the middle plot, and some EMG data for that muscle. So the shaded region is stance, and the non-shaded region is flight. And what we do see is that there are certainly periods during stance of muscle shortening. So this would be the positive power related to what positive power we see in the actuator, the model's actuator. But we also see some periods of negative power, so muscle lengthening as well. So, and by the way, this happens in other animals as well. So this is on the plot in the top right. This is, I believe, a turkey gastrocnemius. So the question is, why doesn't the model capture the fact that muscles might also do active lengthening as well as active shortening? Well, from a work perspective, I think this makes a lot of sense. If you want to minimize the amount of work that the actuator does, you should try and let the spring do as much as possible. Because there's dissipation, you do have to do positive work to balance out the energetics and allow for a periodic step cycle. But there's no reason for you to have to do negative work if the spring can do negative work for you. So I don't think we can explain this negative work phenomenon through a work minimizing lens only. So we have to think about different costs. And in fact, I did tell you that we would consider a couple of different costs. So in this version, we have a work cost and a force rate cost. But I should first probably tell you why we believe force rate should have a cost at all. So there's been a lot of great work recently, actually all in the, well, not all, but mostly in the HPL happening. So this is Tim van der Zee's work with Art Quo. And basically they asked subjects to perform isometric knee torque extension against a periodic waveform. And then they would do that for multiple different frequencies. And the plot we're looking at is net metabolic rate versus those frequencies. And so essentially the outlined magenta region represents this force rate cost. So basically there is additional cost and perhaps more importantly, changes in cost over any other sort of alternative that they controlled for in the study. In another recent study, Jeremy Wong and others used this periodic arm reaching task. So basically people are waving around their arms back and forth, consistency over in time, and at different frequencies, but with amplitude adjusted such that work is held constant in all conditions. And so net metabolic rate still continues to increase even though work is held constant. So there's this additional force that can't be explained by work costs, but can potentially be explained by force rate costs. And then this is a slightly older experiment that basically did the same thing as the arm reaching task, but now with swinging the leg back and forth. And again, work is held constant. So the fact that cost continues to increase indicates that there is another cost not be accounting for. And we believe this cost can be captured with this force rate term. So how do we assess force rate in the model? Well, by adjusting this epsilon, which is just basically a coefficient that scales how much force rate costs there should be per forces of the actuator. And the plot on the bottom shows how energy cost per step changes as we tune up this coefficient in front of that term more and more. And so total cost increases, which is not surprising. That total cost should be proportional to that coefficient. But what is interesting is the blue curve, the work cost also increases. And then the difference between the two is the leftover, which is force rate cost. So what's going on here? Well, when the coefficient is relatively small value, basically we see that the actuator is still only doing positive work, and everything looks kind of normal, kind of similar to what we've seen in the past. But as we continue to crank up the coefficient in front of the force rate cost, a few things start to change. So one thing that changes is the peak force of the ground reaction forces decreases. And because of that decrease in peak force, the average slope of that development of force also decreases. And so this means that force rate is actually being decreased, even as force rate cost is increasing. So what's going on here is as we continue to tune up the coefficient in front of the force rate cost, we make the model care about this force rate cost more, and therefore it's willing to do more and more negative and positive work in order to avoid all of this extra force rate cost that is suddenly so burdensome. And so that's why we see the work cost increasing as well as the force rate cost increasing as we tune up the coefficient. And so notice this force rate cost has now motivated our actuator to do some active dissipation, some negative work, as well as positive work in order to mind this rate cost. Okay, so what about the effect of stiffness? So total cost in this model increases with stiffness with these parameters, and this is largely because force rate cost is increasing. So what's happening here is when you have a stiff spring, you have a relatively impulsive force versus a compliant spring, you have a less impulsive force. And so again, it's kind of similar to the last slide. The effect is such that extra stiffness means more force rate cost, and that increases total cost. And also the actuator begins to do more and more work to start to try and avoid this extra force rate cost. Okay, so now that we understand the effect of this parameter variation, let's go ahead and evaluate how the model compares to some human data in some of these previously looked at metrics. So we have the actuated spring mass model in the top. We're minimizing work and force rate. And then we're comparing to the human in the bottom. Shout out to Arash in the HPL here for sharing some of his experimental data from his paper. So vertical ground reaction forces, they compare pretty well. We think the sort of transient heel strike impact is at least conceptually represented with our collision impulse in the model. And then the ground reaction force looks reasonable. One of the kind of cool things, sort of a smaller nuance thing that comes out of this is this sort of temporal asymmetry where force rises more quickly than it falls off. The power of the leg is fairly well represented. Again, we have some collision loss representing some of the transients early on in stance with heel impact. And the actuator is doing a little bit of negative work and a lot more positive work to overcome dissipation in the model. And then the vertical work loop, now we have some of those nonlinear fluctuations, sort of like this slanted figure 8 shape that kind of represents a little bit of what the human data are doing. So it does a pretty good job of the mechanics, maybe improves a little bit on the work loop. And of course, it can also perform net work like the actuator only model because it has an actuator. So how about energetic cost? Well, let's compare against running speed first. So these are some data from Kip et al. Showing energy cost per time versus running speed. And the model predicts the slope pretty reasonably. And then if we want to consider where is all this increasing cost coming from, we find that there's a good chunk of that is just work to overcome passive dissipation from the collision and hysteresis. There's also a portion of it is from force rate cost. And then we have an offset in there that essentially represents like a basal metabolic rate, or perhaps quiet standing. Okay, so at a speed of 3 meters per second, about 68% of the cost is coming from a work cost. This is fairly comparable to empirical estimates from Riddick and Kuo, which essentially predicted about, estimated about 3/4 of the cost of running coming from performing work to overcome dissipation. That means that 32% of the leftover is from a force rate cost. And most of the change in cost, so the slope of this curve, is really coming mostly from the increase in collisions. The idea is that because the collision loss has to do with momentum and kinetic energy lost at the foot, therefore the faster you're moving, the more energy there is inherent in that mass that loses its momentum and kinetic energy. So that cost really kind of dominates a lot of this increasing cost with running speed. What about if we compare costs for the Margarita data? So the circles are Margarita's data, and the blue is the model. And then if we break down by constituents of the model's cost, so this is cost of transport against ground slope. Again, positive values means uphill, negative values means downhill. So what we see is that positive work does indeed dominate the cost at upward slopes, and negative work does indeed dominate at downward slopes. But one of the more interesting pieces to this is the transition between the two asymptotes, which is a relatively smooth transition that can't just be determined through this idea of doing work to balance out that of gravity. And it's really because of this force rate cost that kind of helps manifest this transition. So what happens is at a slightly negative slope, around -8%, the model has enough dissipation to overcome whatever net positive work gravity is doing on the body as you go down a hill. But the consequence of this is that you need to leverage relatively impulsive ground reaction forces in order to have enough dissipation to do that. And that just means that you have to spend more in a force rate cost in order to do that. And so as work drops to 0 at around -8% slope, force rate cost actually peaks, and that kind of helps manage this relatively smooth transition between the asymptotes. So how does it do? I'd say it does a pretty good job at relating energy costs with a relatively simple model. I'll just go back to this slide that I was talking about in the beginning, where we can start to think a little bit about, maybe speculate a little bit about how some of these effects could be influenced in a model like the one I presented today. So perhaps a real simple one is just the weight of the shoe, right? So we're assuming that the foot has some momentum before touchdown, and then when the heel strikes, it loses that momentum. And of course, if you strap a shoe to that foot, you're adding mass to that foot, and therefore adding momentum that is lost in that transition, assuming that some of that energy isn't returned. Of course, in reality, some of that energy will be returned, but some of that energy will also be lost. So this basically just makes the basic prediction that a heavier shoe is going to result in more collision loss and therefore more cost in your model. And this has already been shown that heavier shoes tend to be more costly, so it's not necessarily anything new, but it's just an example of how we can use a simple physics model like this to think about some of these questions. Another example, I talked about the rear foot versus forefoot running. So in the model I presented today, the transient heel strike impact is captured conceptually with this collision impulse. But of course, in forefoot running, you don't find that transient bit as much. And so this seems reasonable, given that if you land with your heel, then you're sort of basically the mass of your entire foot is brought to 0 or close to 0, versus if you land with the forefoot, only the forefoot bit of the foot loses momentum, and so you could imagine that less momentum is lost. On the other hand, you don't have this negative work happening from collision loss, and so something else has to manifest that negative work, presumably. So it could be that the muscle does more negative work, and then that would have a cost associated with it. Or it could be that maybe the spring does more negative work and absorbs that energy. But even in that case, if you do have hysteresis, you're going to end up losing some of that energy as well. So it may be that some of the reasons the energetics data behind rear foot and forefoot running are somewhat ambiguous is perhaps because there are just different trade-offs of where that cost manifests, even though it will eventually manifest somewhere. Anyway, these are just some examples to think about how you could apply a simple physics model to thinking about these questions. So if you're interested in the paper, you want to read more about it, you can find it at bioRxiv. We're currently in a review in PLOS Computational Biology, so hopefully that'll be out in a couple months as well. I'll acknowledge the lab members of QuoLab for listening to earlier versions and helping me make some decisions about making this a better presentation, as well as some other colleagues I have, Delau Paulette, and thanks to Arash in particular for helping to share some of his experimental data with us so we could draw some of these comparisons, and as well to our funding sources. So with that, I'll take any questions you might have. Thank you so much.
Thank you, Ryan. So if you could now like unshare your screen so we see everyone, it'd be great.
Sure.
Yeah, thank you very much. I also wanted to kindly suggest everyone to turn on your webcam camera during the discussion period. I think seeing everybody usually gives us more active discussion period. Thank you very much for doing it. If you have any questions for Ryan, please use the icon raise hand button that is found if you go click reaction icon at the bottom of your Zoom screen. Now the floor is open for the questions. Actually, let me start kind of naive question, Ryan, because I'm not very familiar with this field yet. So earlier in the introduction part, you mentioned that like simple modeling and complex model, and then you also mentioned that like complex model doesn't necessarily predict the values more accurately. But I just have I wanted to understand conceptually the difference between simple and complex modeling. Like, does that mean like the number of values that the model considers is different, or like what would that mean?
Yeah, so I gave the example of some of the simpler ones, right? In that particular study, the simplest version they had of cost of muscle was just the work done by the muscle divided by the efficiency of that work. But you know, some of these more complicated ones will take into account activation dynamics, you know, or force velocity relationships, or all kinds of things like this. I mean, the spring mass model is, you know, probably about the simplest model you can imagine, which makes, you know, one of the reasons why people like it so much is it's so simple, but it also can do a number of things that people like. So yeah, you know, it has to do with the amount of states you have in your model, the amount of variables you have in your model. And usually one of the problems is the more relationships and the more things you add to your model, typically the more assumptions you need and the more parameters you need to fit different types of data or make these different assumptions. And that's perhaps the biggest problem, is that a lot of times these types of models will work very well actually for the particular question that they were developed for. And that's because there's all these parameters that folks use to help fit their model to their data. And certainly we're guilty of this too, right? We had a few parameters we had to fit as well, right? But the problem is the more and more of these parameters you have, the more power you have to fit your model. And so the problem is then once you take that model out of context and you test it in an independent test that it wasn't necessarily tuned for, they start not to perform as well. And I think that's a little bit of what you saw in that Kolowine study. And then the other problem is, once you find that that model isn't predicting something very well, it becomes suddenly a lot harder to understand why that is, just simply because there's so much going on and so many different aspects of the model that are affecting all of your solutions and the data you're producing. It can be a lot harder to dissect, you know, why something is the way it is. And the hope is that with a simpler model, you have more capacity to do that and understand, okay, clearly when we affect this parameter variation, this is what happens, and we understand a little bit more why. It's a philosophical approach more than anything, but.
Thank you, that really helps me understanding.
Sure.
Kun, you have a question for Ryan?
Yeah, I actually wanted to, my question was exactly, so you partly answered it, Ryan. So I was wondering, what is the critical parameter? Because I noticed that the model predicts or describes these data, human data, quite well. And I guess that the critical parameter in that is probably your force rate coefficient. Is that right? Because
well, it might depend on which particular prediction you're referring to. So,
okay.
Some parameters have more influence on some results than others.
Okay. I was thinking about the Margarita, the uphill and downhill.
Right. So the Margarita, the extremes of the slopes are the easy part.
Sure.
Right, because that's just dominated by positive and negative work, and then at some efficiency. And then the transition is the tricky part. And yeah, I would say that the force rate is probably is the most important piece to determining the transition between those things.
Okay. And then my question is basically, can we think of an experiment, or can you somehow try to verify that parameter independently with another experiment? And one thing I'm thinking of is, we know that, for instance, Jeremy and also Jeremy Wong and Tim Vandersee are doing similar things where they also have a force rate coefficient. And I'm wondering, are these the same for all these studies, or are they different? And what?
Yeah. So part of the challenge is that you can choose many different variations of a force rate cost. That's maybe one of the reasons why the phrasing is somewhat vague. In this particular case, we took the rate of the actuator's force, the first rate, so just one derivative, squared that rate, and then integrated that variable over the entire step. So you can't just draw a one-to-one comparison to some of these other studies, because I think, for example, in Tim's study, I believe they're operating under a second derivative of the force rate, and I don't know if it's maybe the positive bits of it, or maybe it's the absolute value or something. So part of it just depends on the formulation, and then a lot of this idea of exactly how you might formulate a force rate cost comes from John Rabula and Art Kuo's paper showing simulation of similar type of very simple model, where if you choose these different formulations of force rate, you actually get very similar results in terms of ground reaction forces and these types of things. So it's not entirely clear that one is far superior than the other, but it does make a comparison between these different coefficients a little more tricky. Now, in terms of testing the force rate, I did say that the important parameter in that particular case might be force rate, but there is an interesting interaction, because I also said that the reason force rate peaks at this optimal negative 8% slope is because the model uses a particularly spiky ground reaction force to get enough dissipation due to, and this is mostly because dissipation due to hysteresis, actually. So basically you have a spiky ground reaction force, which means that you have to spend more time in the air, which means that you have to rise to a higher height than you normally would have. And then a lot of that height ends up, the potential energy implicit in that height ends up being converted to strain energy in the spring, and then a fraction of that lost to hysteresis. So that's sort of the way that you increase dissipation in the model by having these spikier ground reaction forces at the at the cost of more force rate cost. So I think one simple experiment we can do is just simply to look at the shape of ground reaction forces over these different sloped ground running, and then see if people do something similar where maybe on flat ground or slightly negative slope, people have a spikier ground reaction force, and that might imply that people are willing to spend more of a force rate cost in order to increase dissipation.
Right. Then I will. Then this actually sparked a very brief follow-up question. So what were the free parameters in that optimization? I take it you optimized this model to well describe the data.
Not formally by hand. We just kind of tuned the parameters, right? Because the cost was the cost we were trying to minimize in our optimization was work and force rate. We weren't trying to optimize, say, the error between our model prediction and some set of data, but we kind of just hand selected parameters that would push us into a reasonable range. And the two parameters that we did that with was the stiffness of the spring, as well as the force rate coefficient. And so that's part of the reason why I showed the evaluation of those two parameters in terms of how they affect the model. And we use those two parameters to help us fit the energetics data of the human data we had, as well as the stance time of like contact time of the foot with the ground, also in human running data.
Okay, clear, thanks.
So Art, you have a question for Ryan?
Yeah, it looked like when you showed the plot with the complex musculoskeletal models that they're generally underestimating the increase in cost compared to what humans really do. And I'm just wondering,
yes.
So do you think, well, basically from what you're doing, do you have any recommendations for what those models are doing that's causing those errors? Or does every model have a completely different problem with it?
Sure, let me just pull it up so people can see what we're talking about. Yeah, so it's showing the metabolic data in the vertical axis and the calculated cost from the model in the x-axis. So the fact that the measured data is higher than the calculated cost means that it's underestimating cost, right? And then the question is, have we learned anything from our modeling to suggest why perhaps their models are underestimating cost? Well, one such thing is I don't believe any of these energetics models are taking into consideration a cost for something like force rate. So it's possible that if you added a force rate cost or some sort of representation of a force rate cost to those models, perhaps they do a better job. That's one thing that comes off the top of my head.
And I'm guessing most of these don't have any form of dissipation, or maybe it's not clear if they have dissipation.
You know, I haven't gone through each one to that degree of level, so I couldn't tell you off the top of my head. But yeah, no, I'm not sure off the top of my head, but maybe.
Okay, do I see Kun? You still have a question, or is it just from the previous one? I assume that was the previous one. Yep, I think Walter, you have a question.
Yeah, thanks Ryan for your presentation. I had a couple of questions. The one thing is that through this model, you obviously try to predict energetic cost really accurately, but am I understanding correctly that you're not particularly interested in maybe identifying mechanisms on the muscular level that might actually be responsible for the energetic cost? Is that correct, or?
Well, I guess the way I think of it is mechanisms versus phenomenological approaches is a spectrum, and then I do actually consider this model to be somewhat mechanistic, but it's sort of a reduction, a very reduced version of mechanisms, right? So, you know, for example, some thoughts on the energetics of running. I'm thinking of Roger Crum and Dick Taylor's ideas on developing force and how cost varies with the inverse of contact time. But, you know, I would say that's a pretty, it's a pretty correlational sort of a thing. And I would consider it not to be very mechanistic. And then I would say this type of modeling is certainly a step or a few steps closer toward the mechanistic side. But there's this trade-off between how simple you want your model to be and what level of detailed mechanisms do you want. So where does a force rate cost come from, for example? No, I would say it's not a very mechanistic version of where that might be. I mean, we think of things like calcium transport and that sort of thing. But of course, this isn't a very specific muscle mechanism model. So I don't know. I think it's kind of a nuanced conversation, to be honest.
Yeah, and that's the feeling that I had, that you get, you know, whenever people, because essentially I would say you have kind of a hill type of a model. You know, you have an actuator like a muscle, and then you have a spring like a tendon, and you have a damper like some of the damping elements in muscles. And I just wondered if, you know, how much you relate those to actual muscular components, and how that might potentially explain or help explain potentially, you know, where the energetic costs come from. But I like what you said.
Yeah.
The other question that I had is just a small one. You know, you said at one point in your presentation, you said something like, well, if the actuator doesn't have to do work, then let the spring do work. And I wanted to explore that statement a little bit, because when your actuator, you know, stays isometric and therefore doesn't elongate or shorten, so there's no work performed, does it still cost you energetic cost or not?
So it would depend on which version of the model. Of course, if it's the version of the model where we're only minimizing work cost, there should be no cost to that, right? Because actuator velocity is 0, so no power. But there should be a force rate cost to that as well. Yeah.
I guess that's the argument that I wanted to make, that you know, in a muscle, you know, when your tendon gets longer and then shortens again, and your muscle stays isometric, let's say, you know, it still has to resist the force of the tendon, and that force will cost metabolic energy, even though you could argue the muscle belly doesn't really perform work. I always think of the muscle performing work in an isometric contraction, because, you know, it loads a spring in series and unloads it. So I actually always think that a muscle produces work even in isometric contraction, where the muscle tendon unit is not changing. Go ahead.
Sorry, I was just trying to say I agree with you on all that, and you know, I like to think of it as hidden work, right? Because at the macroscopic level, you don't see anything changing length, but if you zoom in, you do see individual things changing length. And I mean, this is just thermodynamics. At some point, you know, work has to be done somewhere if you're getting a change in energy, right? So. Well,
you know, you have a tendon in series and you elongate that tendon.
And that as well, yeah.
Something has to put work, and presumably the muscle has to perform work in order to load the tendon. Or, you know, if you kind of fall down from somewhere and impact, yes, then of course gravity is there. But still, you know, if the muscle doesn't resist, then you'll never ever get any. Then you never ever get any tendon elongation. The muscle needs to resist somehow. That thing that'll always cost a certain amount. The other thing that I thought was interesting, you know, because in the model there, you know, in latest model is the actuator, where you have a kind of a straight limb and your actuator is straight, you know, then everything is always aligned, like your line of action of the muscle is aligned with the limb. And I was wondering, when people do energetics work, you know, in reality, you know, do they consider that we have a three-dimensional system, you know? So for example, let's say in running, I want to extend my hip at one point, so I'm activating the gluteus maximus, but let's say the gluteus maximus doesn't only extend the hip, but it also rotates it externally and abducts it, you know, does other movements, and they have to be offset, you know, Are those kind of things considered for in these models, that we have to compensate for certain movements because no muscle that I'm aware of only does exactly one degree of freedom and everything else is not there? Do people consider those type of things at all?
I mean, certainly some models will, absolutely. In just like sort of run-of-the-mill standard walking and running, the assumption that ground reaction forces are oriented from in the direction defined by the center of pressure on the ground to the center of mass of the body is actually a pretty good assumption, and does a pretty good job of capturing where the forces are pointed. But certainly there are situations that it's reminding me of, we did a study with James Croft looking at parkour athletes, and they would do this crazy thing where they'd run up the wall. And we had a similar model to this. We didn't have all the springs and stuff, but it was basically what I call the actuator only model, right? And in comparing the orientation of the force vector to that more extreme case, we did find that when the person is on the wall, they were presumably doing something like a lot of hip extension. And I think the idea was that they were kind of like trying to, or actually, sorry, I think it was hip contraction. And I think the idea was they were trying to basically wedge their leg into the wall to get more friction force so they wouldn't slip. So certainly there are some tasks, farther away from things like walking and running, where these types of nuances can play a role. It's just that in walking and running, typically you can neglect these things and it doesn't cause too many problems.
Okay, good. Thank you.
Osman, please go ahead.
Thanks. Thanks, Ryan. It was a great talk. This might be a little too technical, but you've been calling your cost function force rate, but the force rate is in the integrand, right? Not the integral itself. Okay, can you comment on this? Don't you think it should be the second rate of force to call your cost is force rate? Because
if you want to equivocate some sort of accumulated force rate in a literal sense with work, then yes, I agree with you, because you're integrating power and you're integrating some double force rate to get an accumulation of single force rate. That's comparable to work. As you point out, we don't have a double derivative. We just have the first derivative that we're integrating. So it turns out to be some sort of accumulation of force if you think about it more literally. But I think it's a mistake to think about the exact formulation of this force race cost as being a literal thing, in particular because from a practical standpoint, at least, it produces similar results. And then the fact that we need to tune this coefficient in front of that term anyways means that a lot of any differences you might find between multiple derivatives or single derivatives kind of gets flushed out by the scaling of that coefficient. So yeah, sure, if you want to be super technically rigorous, and Art has criticized my formulation of force rate a little bit in the past, so I think he would maybe agree with you a little bit, but I'm not convinced at this point that we can say one version of force rate is the right version or the wrong version. It would just about, if anything, it would be about having more conceptual consistency is all.
I just want to comment on something. You are definitely right. And I've been doing running simulations and you can do both. Means it can be the second derivative of force or first derivative of force in the integral. But what I want to remind is all of our cost studies have the cost inversely proportional to the time, test time. Cost is inversely proportional to the test time, means the cost itself is force rate, but your cost isn't right now. Although you can still do it. I understand what you're saying. I agree with it. But from physiological reasons, if we just match if you want to justify our cost and from experiment says the cost should be inversely proportional to the time. Just a reminder, okay?
I agree. And the last thing I'll say about it is one of the more recent things I've done is implement force double dot or double rate of force into the cost function to be integrated. And it basically gives the same results as far as I can tell so far. And the other thing that's kind of interesting about it is, even though I use the first derivative of force in the stuff I've shown now, because it's squared, you actually still get a similar scaling. So you get Newton per second squared that you're integrating versus the other one, or sorry, Newton squared per second squared that you're integrating, versus in the force rate formulation you're referring to, you get Newton per second squared. But the point is you still get the per second squared part. So actually I can leave the coefficient in front of the force rate term to be the exact same thing, and it gives me almost the exact same result, at least for these data.
I actually have a little question that I might face in the future. You said square. Is there a physiological reason of getting the square other than making the optimization run smoother?
No.
Okay.
It works well, that's all.
Okay.
I see Robert. Robert, you have a question for Ryan?
I'm thinking in the same line as Walter here, Ryan, and you're coming at it, as you described, from a phenomenological way, from the top down, and I'm thinking from individual muscle fiber and tendon up. And the advantage of a model, can anybody hear me?
Yeah.
I've got a message saying
we hear you. I hear you.
The models that you show there with that are more costly, that you just took off the screen, that are more costly than the real situation is more costly than the model, I'm a bit more comfortable with. If I was to look at it, I would suggest that the spring in the tendon is a non-linear spring. For many types of speeds, you might be operating purely in the non-linear range before you get to a more linear range. But let me develop it a bit further, because my experiences in triceps suri and particularly gastrocnemius. Now, there's the general conversation that the triceps suri is the sort of the major work producer, which befuddles me, because you've got the massive muscles above, and it may be that while I can say in triceps suri the tendon is non-linear, the tendon's getting stretched partly externally, but perhaps 50% the tendon being stretched by the active work of the muscle fiber. So it's hard to say that return of energy is an elastic return, or in terms of energy, because you put half of it in with the muscle in the first place. However, you had a figure of the work done in forefoot running and heel-toe running overall, and they weren't much different. So I'm wondering whether the quadriceps are more dominating. I mean, they're the much bigger muscle. And so maybe my conceptual way of thinking that stretching tendons, I find it hard to get the elastic return there because the muscle fiber did the stretch. So you've actually put the work into it, actively. Maybe that's not what happens in quadriceps. I'm not familiar with that muscle. If they're great, big, massive muscle fibers in length, maybe that means that my way of thinking for gastrocnemius is inappropriate. But the advantage of the model, as I see it, is it may not be what you're thinking, but being used as a method of seeing what's happening at the fundamental level. So by looking at the model, it would raise questions and say, well, to me, those earlier figures you showed there had the real life situation being more expensive. So the model says that simple model of a simple springs and linear springs maybe is not working because the real life situation is different. I was not uncomfortable with those figures because I'm trying to break the model down into individual components in the way that Walter was thinking. I guess, is your purpose in making the model to look at mechanistic behaviors, or are you changing the model, which might be able, models can be produced in multiple ways, to changing the model to fit the data, which I think can perhaps, reinforce ideas that are not necessarily right. I'm wandering around here a bit, Ryan, but I guess what I'm thinking is the same as Walter, that is the model being used to predict and break into the mechanisms of muscles, or is it, do you have another purpose? Sorry if I'm rambling.
No, that's okay. A lot. I mean, I think my answer is more or less similar to the answer that I gave to Walter, which is that you can think about mechanisms at multiple different scales, and the mechanisms it sounds like you're thinking about are at the muscle fiber level and these sorts of things. Yeah. I would say I am interested in mechanisms, but this type of model is really addressing mechanisms of whole body physics. I think that's the strength of, let's say, this sort of niche of modeling, is that we can say things like, the physics are such that if the foot is moving at the same speed as the center of mass, and then it collides and loses its energy, this is what will happen, right? Or if you have a stiffer spring, and by the way, the spring is, of course, not a single tendon in my model. It's sort of a composite of all the compliance and elasticity within the whole leg, right? But regardless, if you have a stiffer effective spring, let's say, leg spring, how does that affect the physics, right? So, okay, you have a spikier ground reaction force. You fly through the air for longer and these sorts of things. So although these might not seem like mechanisms to someone who thinks about individual muscle fibers and cross bridges and things like that, I would argue that they are perhaps mechanisms of a different scale. And it's sort of understanding the physical interaction of the organism with its environment, in this case, just a static ground that's at some slope or not. And then that can help point us in the direction of more muscle-based things. And then, of course, we have these different ideas of, as I've talked about, a force rate cost, which might start to point to something happening in the muscle, right? Or things like that. But no, it's not intended to understand very detailed, specific interactions at these very small scales, which are important too. It's just that when you have models that include all these different things, it's, as you say, you'd like the power of the model is the fact that you can pick it apart and understand why one little piece makes it operate in a certain way. And I just think it's a little bit more difficult to do that sometimes, particularly when you're in an optimization regime, because the optimization sort of makes everything, every choice you make in this corner of the space of the problem affects all the other choices in the other space, assuming that there's any relationship between those corners of the space. And so it just makes it very difficult to do exactly what you're saying, which is to pick apart these little details when there's so much going on. On the other hand, if you have, a handful of variables, say, that you can independently vary, right? I mean, just imagine some of these, these more complicated models have, tens and hundreds of states in them. Imagine, and then parameters to go along with them. Imagine if you went and tried and adjusted the parameter for every one of those relationships by hand. You could, it's not very attainable. But in this model, we're still at a level where we can do some of that. And so it's true that, you know, yeah, sure, we can tweak our parameters and then we get energetic cost that looks good. But ultimately, we are more interested in understanding what are the physical mechanisms that have an influence on what those results look like in the end. And so that's why when we do these parameter variations, I think that's really the bread and butter of this sort of stuff, is understanding, oh, okay, if we increase this coefficient in front of the force rate cost, that motivates the model's actuator to want to do negative work and spread out these forces, right? So something like that I would consider to be a mechanism of the physics of that task. I don't know if that answers your question, but hopefully it does.
No, it actually helps me too. I'm still wondering at what stage we will meet, because there's an example, a particular old example that I don't actually agree with, and that is that people have used treadmill work and oxygen consumption work and energetics on kangaroos, and they said, well, look, the Achilles tendon in the kangaroo must be functioning as a great big spring, and that's why it does all these magical things. And when I look at it specifically at muscle and tendon, I go, well, I don't believe that. I think you've got a good spring there, but I think you've jumped from looking at something in a model from the whole animal and then tried to pull out a single tendon and say what was happening. And so I think that I specifically have trouble with that whole conclusion. And I think perhaps you're saying you would too, because you're looking at the whole system behavior and you wouldn't want to pull out a single element. Would that be correct that you?
Yeah, I think we agree to some degree. Yeah, I mean, I have to say, it's very uncomfortable for me to be defending the idea of elastic return in the first place, because I come from a research area where we don't like to think about conservative mechanisms. We like to think about dissipative mechanisms and things like collisions and things like that. And I have to say, I never really liked the spring mass model, because in my mind, you know, if you hold your leg out in the air and you kind of tap it with your hand, your leg doesn't just start oscillating like a spring mass system, right? Like it always felt unintuitive to me and didn't quite feel right. But that being said, I should say, as I've worked on this project, incorporating the combination of these dynamics and looking into some of the evidence more, I'm a little bit more of a believer of elastic return. I just think it doesn't deter much of the mechanics of running. And this is shown when I show the version of the model with just the actuator, right? It can do basically the same things. But it does seem like it should save you some energy. And then we can quibble about how much or how little, I think. But yeah, it's just been kind of an interesting trajectory.
Yeah. Well, thank you, Ryan. That was I think a good answer to a rambling question.
Yeah, no worries. Thank you.
Would there be any last question for Ryan? If not, I would like to thank Ryan again for giving an interesting talk. Next week, we'll be hearing from an invited speaker, Dr. Kelsey Collins from Washington University in St. Louis, and she'll be talking about tissue engineering and regenerative medicine approaches to study fat cartilage crosstalk. I hope you enjoy your weekend, and I'll see you all next week.